Okay, so I think we are ready to start. So again, welcome everyone. My name is Mariangela Pellegrini. I'm the Educational and Patient Program Manager for the ERN-EuroBloodNet. So I'm very happy to indeed welcome all of you, not only from the ERN-EuroBloodNet side, but also from GenoMed4All Steering Committee. To this online educational program on artificial intelligence in hematology, targeting public at large. So indeed, this program has been conceived by the GenoMed4All Educational and Scientific Committee. As you can see, it is an interactive online webinar, and we aim indeed with this program to increase and spread the awareness on this growing role of artificial intelligence for medicine, so for diagnosis, treatment, and follow-up on the three different clinical domains of hematology. So as you may know, this program consists of 4 webinars. Each webinar is provided by key expert in the field, so in the application of artificial intelligence on rare hematological disease. The program has started on the 13th of September, and we had already 2 lectures. So the first one was on GenoMed4All ERN-EuroBloodNet for precision medicine hematology. Then on the 27th, we presented the use case challenging on MDS, sickle cell disease, and multiple myeloma. And today we are going to talk about data standardization and linkage, so standards and federation. But before arriving to today's lecture and introducing you to speakers, I would like to share with you some home rules. So first of all, as you can see, this session is recorded because the videos of the webinar will be implemented in our e-learning environment, both from GenoMed4All and ERN-EuroBloodNet sites. So if you don't feel comfortable with that, you can switch off your camera, change your name, or just notify to it, and we'll take care during the edition. Secondly, your microphone are muted and they will be muted along all the presentation. But as you can see, there is a QR code displayed and also website link displayed on the screen. It's a Slido. It's a polling tool for gathering question. So please use it for collecting your comment, feedback, or question during the webinar. All those aspects will be tackled at the end of the presentation. So we will take care of each comment and question you may write. Also, of course, at the end of the presentation, if you wish to unmute yourself and take the floor, also this is very welcome. Said so, we can finally arrive at today's lecture. So as said, we will talk about data standardization and linkage, so standard and federation. With us today, 3 case speakers as said, so Silvia Uribe Mayoral, Vincent Planin, and Davide Piscia. For introducing them very quickly, so Silvia Uribe Mayoral, she's a telecom engineer and she has also a master's degree in communication technology and system. Since 2021, she works as assistant professor at the Escuela Técnica Superior de Ingeniería a la Universidad Politécnica de Madrid. Vincent Planin is a graduate in Lyon in stellar imagining. And after his initial career in telecommunication, he works now as a technologies expert in the Central Global Consulting and Solution teams. And finally, Davide Piscia, he has a PhD in thermal engineer and he leads the data platform and tools development team at the CNAG when he coordinates the work of a team of 13 software developers and engineers. So please, the floor is yours. So I think Silvia go first. Thank you very much.
Thank you very much. Thank you. First of all, we would like to say thank you to the organizers for being part of this program. Well, in this session, we will go into an important issue that affects our field of work, study and research, the disparity and scarcity of the data in rare diseases. For doing so, the presentation will be composed by 4 main topics, as you can see in the agenda, with the aim of setting the stage for a discussion on how we can bridge the data gap between, in rare diseases, turning this into a challenge, turning this challenge into an opportunity to transform the healthcare in this area. So our agenda today is divided into several key segments or parts. In the introduction part, we will go from the initial problem statement to the opportunities that we have in here. Then following the introduction, we will dive into the GenoMed4All approach from 3 different perspectives. The first one is related to the fact that one of the main challenges in addressing data disparities is the lack of standardized data. In this part, we will explore the challenges of data harmonization and the need of defining a common data model that will bring us consistency for our data. After this, we will discuss the design and development of our platform that we will enable collaborative analysis without compromising data privacy. And finally, we will go to present how we can use this platform. Finally, once we have presented the GenoMed4All platform approach, we will go for the conclusion and lesson learned, where we will summarize the key takeaways and lessons learned from the almost 2 years that we have from the project. And finally, we will be open for all of your questions. So before we go into the details, let's remember that our goal today is not merely to identify the challenges about the scarcity and disparity of rare disease data, but also to highlight the different opportunities that this situation can bring us. In this regard, in this environment, data collection and analysis play a crucial role in improving medical data, and we need to have this in mind. So, as you already know, in the hematological area, a majority of diseases have a genetic basis. In this domain, we find ourselves facing a complex landscape of up to 450 genetic variants, including both oncological and non-oncological conditions that represent an important growing public health challenge. So in our attempt to combat these diseases in the most optimal way, precision medicine has emerged as an innovative option. However, this option presents some problems that we need to be aware of. In this regard, the application of precision medicine in the hematological area is affected by several critical challenges, where the most important one can be the lack of a well-established international data set to be used for research, diagnosis, and also for treatment. So, in the world of rare diseases, such as the one considered in GenoMed4All, specific situations have to be taken into account. The first one is that the data is often scarce and fragmented across multiple sources. Adding to this complexity is the fact that the rare disease research involves multiple data modalities. We must consider not only clinical, but also genomic, demographic, imaging, and other types of data. These different streams of information are essential for gaining a holistic understanding of the diseases and defining the different solution for each of them. And finally, there are different approaches to the data standardization. Concepts like OMOP, FIRE, and phenopackets bring their strengths, but also their complexity to the table. So where to go from here? How we can beneficiate from the potential of precision medicine in the hematological area with these essential pieces of the puzzle are missing. In this challenging landscape, clinical networks play an essential role. Networks such as EuroBloodNet, which can present a main proof of the power of collaboration. But however, from the technical point of view, we can think also about an optimal solution, which is the pooling and integration of multiple data sets from different centers. But this option faces significant resistance in the healthcare context. So it's important to be aware of the main reasons behind this resistance in order to consider all of them. So we can categorize them into 4 main areas. We have reason from the economical and motivational part. We have also reason regarding the legal and ethics. We have different reasons that avoid this sharing data from the technical point of view, and we also have some reason from the political point of view. In a world where the data is often considered as an important commodity, maybe there are some economic interests that can sometimes avoid this data sharing. So we need to have this in mind. Data sharing is also related with the legal and ethical problems, concerns about the privacy of the data, the intellectual property rights, the potential misuse of the data, often lead to this kind of resistance. There are also technical barriers that can also stop this data to be shared. And finally, the political landscape can play a significant role in sharing or not sharing the data within this environment. So having this in mind, what is the innovative approach that offers a solution to these challenges? We have found a very important one, which is called federated learning. Federated learning allows us to train AI models across distributed data sources without having a central node with all of the data. So this means that instead of bringing the data to the model, we bring the model to the data. So we can allow the preservation and the security of this sensitive data health information. So in conclusion, to solve this challenge about the promotion of the potential within federated health data repositories, we must think outside the box. Federated learning represents an scalable and privacy-preserving approach that empowers us to train the AI models into a collaborative way, while this privacy of sensitive data is assured. So for this reason, federated learning can be considered as the basis of our approach in GenoMed4All, which is going to be presented next.
Thanks very much, Silvia, for this introduction and the positioning of the different problems that we had to work on this very interesting project. So data standardization is a long story along the evolutions of the technology in the healthcare IT domain, because from the beginning of this business domain, I would say 20 or 30 years ago, we already faced the problem of data heterogeneity and disparities. So could we go to the next slide, please? Why? So we intuitively, we need harmonizing data into a project like the one we're working on based on federated learning. It's intuitive because as I shown, and I come back on this federated learning concept that has been presented by Sylvia. Federated learning concept means that, as she said, we bring models to the data, which means that we must distribute models versions to the different contributor of a network, and we ask this contributor to train their own version of the model and propagate back to a central server an updated version of their own model training. So that means this model exchange means behind the scene that there's a lot of problem around data which are feeding the algorithm, because as we all know, there is no AI if we don't have data, which is at the source of the model training. So training models mean having data, and we have obviously identified from the beginning that there's a lot of heterogeneity of data across the different contributors of this project. So we had to face this consistency and harmonization in order to address the AI model training and distribution pushed by the federated learning concept. The second reason why data harmonization is key for this project is because of the scope of the data type which are addressed for training the model. As it has been said at the introduction of this webinar, we are focusing on rare hematological disease, and the scope of data that are captured and used for treating and developing decision support or predictive model around this disease is wide. We have images that are capturing the cells details, the size of the cells that are analyzed by the searchers. So we have image data, and we have feature extracted from these images that can be used. We have also, and that is very important in this project, we have access to the clinical history of the patients. So clinical data, which are referring to the studies, the tests, the questionnaires, the observation, the treatment, the diagnostic, all information surrounding finally the pure disease itself captured by the image, and that may serve the model development and the precision of the final result. We also, and this is a key challenge in this project, we're also tackling genomic data, which are very important for rare disease. And in this space, there's a range of data type and data representation that we have to tackle. So 3 dimensions of data may need to address, which increase the need for harmonizing all of this information. The third reason why we need harmonization is because the systems, the health information systems, which are storing currently this information into the different hospitals, are very often always coming from multiple vendors. And the vendor space of health information system is very fragmented and very proprietary. So each vendor has its own way of formatting the data. And this way is not the same as the other or the competitor, obviously. And so when we try to aggregate all this data in order to train a model, we are facing a lot of heterogeneity between these different sources of record and HIS systems. So that's the main 3 reasons why harmonizing the data is key, and we had to address this problem. Could we go to the next slide, please? So harmonizing data, what does it mean? In fact, it means agreeing or defining or deciding on a common data model. So what is a common data model? A common data model is a way to represent, I would say, concept into the healthcare domain in a wide manner. So When I say concept, it may be how do I represent a diagnostic? How do I represent medications? How I describe an observations? How do I describe the procedures? And so on. So this how to describe is something that has been analyzed and addressed by the research community for decades. And we thought that in this project we need to define and decide on a common data model, and again for three reasons. Because with federated learning, we need to train a model at the beginning. We have to create a seed, first version of the model, which is propagated and trained by everybody. And to develop this model, we need a reference of data sets to submit to the model. And this reference of data set has to be as large and as representative as possible, because it's going to be trained on the different edge system. That's why we thought we need, even for starting the first model development, we need a common data model reference. So that's the first reason. The second reason is that as we understood, the AI Federation is engaging multiple care providers and hospitals in the training process. And for these hospitals to be able to train their own instance of the model, they need also to extract the data from their health information system, from their PACS, from their genomic data bank. And each of them has to do it in any case for training the same model in some way. And if we propose a common data model, which is the same as the one that is chosen into the central server for training the seed, so the initial version of the model, then we facilitate a lot the extraction of the data, because everybody is speaking finally the same language. So if the data science or the data engineer into the hospitals has questions about specific information, he can use this common data model definitions to queries the data scientist or understand clearly which data is expected for this model. So that's the second reason why we need a common data model. The third one, which is more subtle and perhaps more not so easy to understand, but for training a model, you need to extract the data from your data set. And we propose with this project to define what we call the extract, transform, learn process, which is the process for extracting this information. And by using a common data model, we can provide to all the hospital the same ETL, because they are using the common data model behind, and they don't have to invest on extra effort to extract this data for the model. We can provide them attached to the model an extraction tools which facilitate a lot and speed up the data extractions from the source of record. So these are the three reasons why after harmonization we need to choose a common data model. And then the third question we had was which data model to choose. And then again, a complex question that we had to work on with Sylvia, Davide, and everybody in the consortium engaged on this work package is again a disparity of data models coming from the community of research. So when we look at genomic, I would say the picture is in some way very clear, because the genomic pipeline processing world is well structured and well known by everybody, which are mainly applying the same macro steps. So for each of these steps, you have a format of data. You have FASTQ, you have BAM, you have SAM, you have VCF. So all of that is well structured, but already fragmented, but well identified. When we look at the clinical data and try to find a common data model which could embrace both the clinical data, both the imaging data feature, and also some part of the genomic data, then the situation becomes more complex. And we have identified three outsiders in this selection, one which was OMOP, another one which was fire, and the last one was phenopacket. So we conducted a very deep analysis based on the use case we have, the feature that we must extract, in order to identify what is the best standard we should choose. At the end, the selection has been, so on the right hand side you have a diagram which is the bottom right diagram, which is extracted from a paper that we have published, a journal that we have published, which illustrates all of this analysis and detail chose selections criteria process, and it presents the capability of this model in regards to the different usage of the data, from the raw data to the up part of the usage of the data. So at the end, we have chosen FHIR as a common data model. FHIR is very well known as an interoperability model, data exchange models. It has also its own common data model, and we have partially chosen this common data model for this double competency, because we anticipate with this project future data exchange and with other European projects, and FHIR was also a very good candidate for addressing these needs. Next slide, please. Yeah, a last look very quickly at this data extraction from source of record problems that I've mentioned in the previous slide. Here we shows roughly what are the different modality of data integration that we had to take into account in order to feed our common data model into the hospitals. So at the bottom, you have imaging and genomic data that are extracted from the packs or the genomic data bank, and which are going through a feature extraction data computing activity with guidelines provided by GenoMed4All, of course, in order to extract the feature that we are looking for. And these features are populating Excel files that are then used for feeding the local data model. On the clinical data, we have essentially mostly the EHR, so the health information system as a source of information. And what is done is that we are following the standard research process, where you have a clinician which has the ability and who is granted to access patient identifiable data and who has the knowledge of the data, accessing the health information system, the EHR, and populating various systems depending on our partners. It may be a REDCap, it may be an EDC directly when the care institution has a real clinical trial management systems. It could be also a RADIP data platform, the case of a EuroBloodNet, for example, that produce Excel files. And again, we have a transformation process which take these different information and transform them to be harmonized into the common data model in FHIR that is used for the project. The floor is to you, David.
Thank you, Vincent. Thank you also, Sylvia. So I'm going to try to explain how we build the federated learning platform, what was the rationale, what was the path that we followed. So one of the first concepts that I would like to express that it's a quite complex project endeavor because of different factors. One factor is that, as you may imagine, the platform is a distributed system, so there are different actors which are living outside, in different places. So we need to take into account this. Also, is an asynchronous platform because basically, when we want to run a training, so we need to get hold of some computing resources which might not be available. So we have put together like a buffer module, which basically is a queue. So when you want to train a model, then you create a job which you go to a queue, and then once the resources are available, then the training is started. Also, it's complex because but it's a research project, so we are trying to do something which has not been done a lot in the past. So there are no mature architecture that we can have a look at it or be inspired. So we had to, discover new things, try to innovate a bit. Another complexity, as you might imagine, that the requirements that we need to build a platform were not completely fixed at the beginning, because some requirements are were the output of work packages. So we needed to synchronize with other work packages, try to communicate with them what they need and what we need to know. So that was also a bit complex. And then, of course, because we handle sensitive data, genomics, medical, clinical data, so the platform has to be very secure. So this is also an aspect that we need to take into account when we plan and then when we implement the platform. Two main objectives that we had in mind when we start building the platform, that was that the platform needs to be flexible, because these different requirements that we get, and also because in the future we might need to serve different use cases that we are targeting now. So the platform can be very rigid, but it has to be flexible. And also another important point that this is a platform that we have been building within a European project, but of course we would like that this platform is going to be used also when the project is over in other at least research projects. So is something that we would like to be easy or possible to be sustained in the future. So because of this, we have chosen different modules, but all the modules are open source software. So it means that we are not locked in by some vendor. We are not buying licensing from a commercial provider. So we think that is a good way to move forward. Also, we try not to reinvent modules or part of functionality that has been already developed outside in the community, because we are not 100 software engineers, so we are limited resources, and we try to take a maximum profit of what is already outside. And also, because of this, we need to build something which is very modular, so there are different pieces that can be plugged in and eventually replaced if we see that a module is not working as we expect. Thank you, Silvia. Thank you. So, as the core part is the federated learning, so which is the process where a central hub move model weights into the different nodes, and then gather also the result of this training, and then do some aggregation, and then move it the model weights again to the different nodes. So all this is quite complex from a communicational point of view. So we had to look for a library which takes care of this. So at the end, we chose an open source model library which is called Flower. But during this process, we have extensively reviewed also different options. So we had defined a set of criteria, and we evaluated the different options. At the end, based on the result of all the criteria, we have chosen Flower, which is indeed open source. It comes from a research environment, but it also has a commercial support if needed. And it's a small library, so it does only one thing, but very well. So a very low-level library. And then it's very flexible in the sense that we can use different Python model libraries. So there are, there are TensorFlow, PyTorch, JAX, and all these are compatible with Flower. And also is very performant because it uses very good low-level communication protocols like a gRPC and protobuffer. So this is the diagram that we try to explain visually what I have been trying to explain, with text. So basically, you can see that there are 3 nodes, which are called local age in this case. And you can imagine this like being mainly hospitals, so a department within the hospitals. And then you see there is a central server where everything starts. So the central server communicates to the different nodes, sending the model weights. Then each hospital, each local age has its own data set, which share the same common data model as Vincent explained, but the content of the data set is different. So the same model is trained on different data set, and then all the results are gathered together. On the central server, there is some stuff occurring, so aggregation, checking, quality, and then it's sent it back again to the hospitals. Apart from the Flower, which is the federated learning library, so we needed to choose different modules, as I mentioned before. So we tried to put together like different bricks, and one important piece is the server. So the server is the module, the software that allows to communicate between different nodes. So we need to organize quite a lot of communication between the central server and the different nodes. So we need standard communication, and for this we are using FastAPI, which is an open source Python-based web framework, which is very popular, especially in the machine learning community, and it's provide also some good feature like automatically documenting very well the APIs that the system has to use. And then we had to also create some user interface. So because we want to do something also user friendly, which has to be responsive, which has to be have a nice aspect. So as a framework, we use the Vue, which is also an open source, very popular web framework. And then another important aspect in how we manage the life cycle of a machine learning or AI model. So again, it's a complex task which requires a lot of steps. And on this part, we rely on another open source library, which is called MLflow, which is very known also in the machine learning community, and we plug in into the platform. Then we need also to have some persistence, so store some metadata. So basically, not the data set itself, which they stay on the hospitals, but we need to store like the metadata, so the data that describes the data set, or we need to store how a training task is configured. So for this, we needed a database, we chose PostgreSQL. Then there is something difficult, which is try to install something that is working in your environment, which is controlled, install the same modules in somewhere else, like in the hospital. So for this, we try to virtualize, so to use something called container, which is a way that it's easy to reproduce the same environment in different parts, so within the hospital without having too much difficulties. And then the last aspect that I want to mention that we use as an identity provider Keycloak, which is an open source module developed mainly by Red Hat, which is very robust and is very popular also within the research community. And also it's quite easy to, if in the future we want to connect or federate this identity provider with the lifecycle AI of the European Union, then it's something that has been already done. So it's something that we can also provide in the future. So the one is the last slide. Silvia, I don't know if you want me to explain or you want to explain it? I can go?
Yeah, please.
Okay. So on this diagram, we try to put all the modules that I explained before. So you see Docker is the virtualizer. Then you see the central box, which is the red orange is describing how the training the training is done, no? The model training. So you see the communication is via gRPC, and then you see that there are in the big central green box, there are the fast API, which connects to the yellow box, which are the hospital. No? They also have the fast API server. And then you can see that the big difference between the hospital box and the central box is that in the hospital, there is also the ingestion pipeline, so the data provisioning. So basically, all the structure, all the infrastructure that you need, to provide to generate this data set that then will be used for the AI training. And then you can see that the module like MLflow or the Postgres are only on the central server because the model lifecycle is managed at the central place in this case. And then you can see that when there is a mention to Kong, which is a proxy server in front of the infrastructure, which make easy to secure the communication between the different actors of the infrastructure. So I think that's all for this part. And I'll start also the third section, which describes how we use the platform, or how the platform is intended to be used. So maybe from what we have explained before, basically there are two big parts that together they are the platform. So there are the machine learning or federated learning platform, and then there are the data provisioning part. They need to be connected because, as Vincent mentioned, the data is the core part of the AI. So we need to have something that provides accurate data in the same data format. So this is the data provisioning part. And then once this data set has been generated, then we can use the machine learning training platform to train the model on this federated data set. So the two parts run at different speed, in the sense that you can imagine that data provisioning needs to start from when the raw data is generated. So in the case of genomics data, when the sequencing has been generated, so from the FASTQ, and then move from the FASTQ to the variants. It can take, depending on the infrastructure, on the size of the sample, it can take hours, can take some days. So it has a time scale which is different from what is required from the platform. So basically, the way we connect these two different worlds is that once a data set has been successfully generated and inserted in the common data model, then is extracted as a data set, which is usually a CSV file. And then this file data set is registered into the central platform. So the central platform is now aware that there are this data set with this metadata, which is available for training. There are different users which interact with the platform. And one is, of course, what we call data custodian, or the data owner, is the person that can can register the data set into the platform. So what she needs to do is basically understand if there is already use cases defined within the project that it can be leveraged, and then it can get hold of the same analysis pipeline which needs to be the same for all the same use cases. So it will or she will run this data set with this standard pipeline, and then what the results of this pipeline will be uploaded into the Fire server, which is the common where the common data model lives, and then it will be extracted from the Fire server and generated a CSV file, and then the data custodian, or helped by the data engineer, he could register the data set in the federated learning platform. Then another use case is another user will be, of course, the data scientist. So a data scientist that wants to create a new model or test a new algorithm, he or she will have to do like basically two steps, one outside the platform and one inside. So outside the platform, the data scientist it will need to get hold of a synthetic data set or a public data set. We describe is representative of the use case that she would like to tackle. Then she will start developing locally an algorithm, a model. Once this model is working fine locally, he will try to federate it or simulate the federation locally. And then before uploading this model to the federated learning platform, she will need to use the validation protocol, which is something that GenoMed4All is working on. So it's a way of ensuring that the model is properly federated, that is going to give a good result once it will be deployed into the central platform. So this is still the data scientist. So once he validates the algorithm, the model, he can now upload the model to the platform, select and then he can generate a training. To generate training, he will need to select an algorithm, a model. From the UI, select a set of data sets, configure the parameter, then run the training. And then once the training has been finished, then he could check the result of the accuracy and validate the model. And then the last use case is something that we haven't implemented yet, but is basically the clinician. When he will be able to use the model validated and trained on the federated dataset, he could use this model to predict. So based on their input data. But this part is something that we need to discuss with the clinician. We did a GenoMed4All project, and we need to see how we can implement this feature out in a way that will be useful for them.
Yes, thanks very much, Davide. So to finish with this platform usage third part of this webinar, here is a diagram which summarizes, in fact, into a synthetic way, in fact, the different dimensions around this platform. So we have a solution component dimension where we recognize the different elements. I'm going through that quickly after Davide. We have a data flow dimensions that shows how the data are flowing across the platform. And we have also a user dimension. So who is doing what, as Davide currently explained. And this diagram has the objective, in fact, to synthesize all of that into a same picture. So back to what Davide is saying, and not overlapping what you have already described, but on the left-hand side, you have the different contributing hospitals. So here we represent only two, but each of these hospitals have their own source of record, as you see on the left-hand side. So if I look at the data flow, it's going through the left to the right. So the source of record coming from the data source of the hospitals. You have a first platform component which is in charge of this data extraction that we have discussed previously, and which is, as I explained before, using either ETL, RADIP, surveys, or EDS. and you have the common data model into the hospital, the contributing hospitals, which is based on FHIR, and which consolidate all of these data together into a single data model. Then arrive here the machine learning worker, which is the federated worker that Davide has presented just before. The input element of this worker are the data sets which are extracted from the common data model and which are containing, I would say, the normalized data for the trainings. When I say normalized, it means the gender is not female or male. It may be 1 or 0. The sex, the gender, or we may have other attributes which are normalized into a way that it can be easily understood by the algorithms when it trains the data. And the space of this worker is really focusing on 3 functions, as Davide said: checking the quality of the data in order to validate that the proper data, the data we are pushing to this model will not introduce a BA or deviations on the final training. Of course, work on the training activity for the models, and also, as Davide said, validates that what is produced by this contributor, a federated learning contributor, has the right level of quality and accomplishment. Then once an hospital has trained its data, it pushes its individual models to the central server that we have discussed previously. And the central server is the second part of Davide development and all his teams who has worked on this framework. It is the part where you orchestrate the activity of the different contributor, the workers. It's the place where you assemble and the different contributions into a single model. So that's where you aggregate, and that's the heart of the federated learning concept. So you aggregate the contribution of each of these contributor, and you need to validate incrementally that these aggregations is fitting quality and expected outcome. For example, do not introduce again specific BAs, because you have different hospitals providing their own feature, but not all the hospitals have the same amount of data. You may have a big hospitals which produce a very rich individual model, where you have another hospitals who are receiving less patients, who may produce another version of the same model trained differently. So when you aggregate all of that into your federated learning manager, you need to validate that this integration takes place correctly. And then, as Davide said, there is this broadcast activity to send back the new model version to the hospital clinical decision support team, such as it can be used by clinicians. That's a step that we didn't reach yet, because this model has to go through medical device validations, as it is an AI which support the decision activity of the clinician. It has to go through specific criteria of validation, like medical devices that are currently also standardized by the European Commission. So we are not at this stage yet, but the models, the data flow is already in place. So that's for data flow dimensions. For data flow and component dimension. Now, from the users, I don't repeat what Davide said, but we have the clinical researcher, which have the ability to extract data from the source of record and populate the data model. You have the data engineer in the middle, who are taking care that the training is running correctly, checking the quality of the data set, executing the training and validating the model outcomes that they can push to the central system. This is a key function, because that decides on the quality of the final model which is aggregated. So it's a key function. And on the right hand side, you have data scientists, of course, which are working on this model aggregation and checking that the quality is always the one that is expected and that there's no deviation. So 3 main roles of users on the platform, which is distributed, as we see here, between a central system on the right-hand side and contributor workers, which are distributed across the different hospitals. So that's all.
Okay, so thank you very much, Davide and Vincent. Once we have presented the main objectives and also the general approach of the GenoMed4All federated learning platform, we would like to share with you some lessons learned that we have from these months of work. The first one is that one of the main lessons learned that we have is that the gathering requirements from the different stakeholders is not a simple task. In this environment, we have several different kind of stakeholders with different knowledge. So it's very, very important to bridge the gap between the technical expertise that we have and the domain-specific knowledge of the clinicians and so on. Our second lesson learned that we like to share with you is that our experience has revealed that designing, implementing and deploying a platform like this one is very, very complex. So it is important to have the necessary infrastructure in place to make the development, the integration, the testing and the deployment easier. The third one is that we have come to understand that a close collaboration with the IT department of the different hospitals is crucial for the deployment of the solution. Their expertise is essential in ensuring a smooth deployment of the solution. Perhaps one of the most critical lessons learned is the importance of the data provisioning that my colleagues has mentioned before. Collecting the initial data set for the deployment, for the development of the initial models, but also collecting the different data to be included in the data set in the hospitals is a very important task and a very, very complex one. And the transformation that is needed to be performed to have all the data into the right format for the AI training is vital for the success of the platform. So this is, I think, one of the most important lessons learned that we have from our experience in this project. And I think that we all like to thanks to the organization and also to our colleagues in the project for their work. And thank you so much for your attention. And we are here. If you have any kind of questions, please go ahead.
Thank you very much for this comprehensive presentation, Silvia, Davide, Vincent. Thank you so much. So I would like to check with my colleague Diana if we can display the question, if any, gathered on the Slido. Thank you. So we go with the first one. Nice presentation. I echo the same. Have you tried deploying new edge nodes in this current federation? And if so, how do you handle disparities among them on, for instance, data quality?
Well, I can partially answer to that. The project has a limited scope in terms of partners at the moment. So the partners which are onboarded on the project are going to deploy the current workers, federated workers into their institutions. When you say, have you tried deploying new edge node, I understand the question as other hospitals which are not currently in this perimeter? The answer is no, because the project maturity has not reached its final stage, but that is the objective, in fact, to define a kind of a protocol. It's not a protocol which allows the introductions of new partners and new H node type into the federations for a given algorithm. And the consortium has worked on that in order to define what are the different steps. And in this process, validation process for new nodes introductions, they are clear, well-defined space for assessing the data quality that is proposed by this new contributor, but also its capability to train the models, because that may, depending on the model itself and the data, we have genomic data processing, so we may have potentially problems there. And it's also its capability to extract the required data for the model from its source of information. So in this space, a capability to deploy a FHIR common data model and then execute the ETL on top of this common data model. Yeah.
Thank you so much. So if Silvia or Davide don't want to add anything, I will go with the second question. My question as a clinician will be if this federated architecture means there be no need to anonymize the source data anymore, since only the model moves.
Silvia, I can answer up to you, Davide or Silvia, but
you can go if you want.
Okay. Yes, that's the principle. In fact, as the model is moving to the data, we don't have the need to anonymize the data before training the model. But we must be conscious that this concept has some subtleties if the number of information that are provided to the model when it is trained at the edge is very small, because then you increase the risk to re-identify potentially a patient into the model data that are being brought to the central systems. But in theory, this is one of the big attractions and big added value of federated architecture. Data are not moving outside of the organizations where they've been produced. So there is no need for anonymizing this data, because we are not concentrating and aggregating all of this data into a central space for training the model. The only place where we need to anonymize the data, and we had to do that for this project, is for creating the first version of the model, to create the seed that is used as the initial model version, which is used by the different hospitals. Because then here you need a reference data set, which is developed by the data scientist into the central place. And for that, we had to ask the different hospitals to contribute with anonymized data set, pseudonymized in this case, but anonymized in the main concept, in order to develop the first models. But once this first model has been developed, the concept proposed to not anonymize any new data when they are used for training the new version of the model at the edge. That's the big attractions of the federated learning, yes. And that's why this project has a lot of potentiality, in fact, in the future, because we are addressing a data privacy issue that is at the heart of the cybersecurity department of every hospital.
Anything else to be added from the other speakers, or other question from the audience?
I agree with Vincent that maybe we should, the people that develop the model should take care that the model doesn't leakage any information somehow. But I guess that the point that within a control network like it is this, I think there is very low probability that this is going to happen. But then if you have an open network, there are a lot of actors that you don't control, then you can add differential privacy. You can add there are way of try to mask this privacy also further. But I think within a control environment, I think there is no need to. There is not this risk.
And also, there is a last dimension that has not been presented here and also really developed with this project, and which is related to federated learning. In the near future, this technology, I'm convinced on that, will get more and more attractions on the community, in the wide sense, on the community of scientists and data searchers. Nevertheless, when we consider rare disease, this is a concept very attracting because you have a lot of disparity in terms of data volumes across the hospitals. You may have a big hospitals which has the capability to have perhaps 100 or 200 patients affected by unfortunately by this disease, and you may have 5 or 6 or 10 patients to a smaller hospitals, but that may be very valuable also to contribute to the federated learning. So rare disease is very interesting. Is a very interesting use case for applying federated learning because it allows these different entities to work together. Nevertheless, what we see potentially arriving, and it has not been addressed in this project, is the rewarding in some way. Because if you have a very important hospitals, which is contributing massively to the training of the model, it may be in a positions to ask for some potential reward in regards to the resulting model that has been produced. This is not the case at the moment because we are in a public community, public hospital community mainly, that are for the moment openly contributing to this objective of training model. But if we apply the concept to a wider community, including private actors and so on, we will have the questions of rewarding depending on the contribution that each organization is producing for training the model, which is a very interesting concept to be consolidated. There are already research papers which are looking at that. We have not addressed it, but that's a vision, and that's a challenge that we see ahead to be addressed certainly at a time.
Thank you very much. I think all the questions have been tackled. So thank you very much to the 3 speakers for having shared their knowledge and expertise and time with us today, and also to the audience and my colleague of Australo team also for the support. Thank you very much.